pleasure to introduce Ravi. You know him already. Ravi did his PhD in Chennai and postdoc with Kochen-Specker Institute. He has come here and he will teach us about contextuality in quantum theory. And maybe I should tell you a little bit what he's working on, what he's planning to work on while he's here. Well, basically, his work has been largely about contextuality or non-contextuality, and that's what we will learn about today. He has very interesting ideas about how to quantify non-classicality most generally. And one of the things that he has proposed to do as part of his postdoc is actually to characterize non-classicality in this paradigm of indefinite causal structures which I work in. There's some pretty original ideas there, but this will not be about this. Today we'll hear about contextuality.
Thanks, Ogden. Well, welcome everyone to my first seminar here. I've been here a month now, so I know almost everyone. I think Serge I'm meeting for the first time. But yeah, so I want to tell you about some work that I really started during my PhD, but only recently did I manage to publish the final paper in this set of 4 papers, which comprise, it's over 5 years. So there's a review sort of talk, an overview talk. So I'll give you a big picture view of what I've been up to, and one of the main things I've been up to. There's a lot of small side projects that I've also done. And it's mostly about contextuality. Presumably, people here are somewhat familiar with the word or the notion in quantum theory. Have the core? No, I will. But I just want to know what the general do people know the Kochen-Specker theorem, for example? Okay, that's a good metric, for example. Okay, so. You don't know it? Okay. Yeah, okay. So I'm going to try to introduce everything. So the story of the Kochen-Specker theorem is, broadly speaking, that in the 60s, there were 2 sort of major no-go theorems in quantum foundations that were discovered. One was, of course, Bell's theorem, which I presume everyone here knows about. Bell's theorem. Does anyone not know about it? Okay, so right, because everyone's at least heard about it, right? And this was in 1964. The Kochen-Specker theorem was 1967, and it's in some sense a cousin of Bell's theorem, but it also applies to single systems, and you don't always need 2 parties. And the genesis of the Kochen-Specker theorem actually goes back to 1960, which when Ernst Specker wrote a paper which was about he called it, at least in English translation, the logic of non-simultaneously decidable propositions. So that's just a brief historical context of when these results are from. And so of course we know that Bell's theorem has seen a lot of a transition from quantum foundations to applications in quantum information. And so today you can, even computer scientists know about Bell's theorem. They don't need to necessarily worry about quantum foundations, but they'd still talk about Bell's theorem in terms of, the difference between shared classical randomness versus shared entanglement and things like that. Without necessarily worrying about what this means for the nature of reality or whatever else, right? The same thing hasn't happened for the Kochen-Specker theorem in some sense. People have tried to propose protocols for what you can do given, I don't know, the Kochen-Specker theorem, but there are some major hurdles to being able to actually use them in an experiment, because there's issues with experimental testability as well. I'll come to those as I go along with my talk, but let me just begin, I guess. I already gave you an overview. Here's a rough outline of how I'm going to structure this talk. So, motivation is simple. It's just to try to understand what non-classicality in quantum theory is, and in a certain context. I'll introduce this framework for contextuality that was introduced by Rob Speckens in 2005, and which forms like the philosophical basis for this work in some sense. So after I introduce this framework, I'll go back to. I'm not really going to talk about Kochen-Specker until here, and then I'm going to tell you about Kochen-Specker contextuality and how that fits within like this broader framework. And we'll talk about a graph theoretic framework for Kochen-Specker contextuality, which is due to Cabello, Severini, and Winter. So I'll briefly introduce you to that. And then I'll point out things that are sort of, in some sense, missing in that framework. Like, namely, if you wanted to be able to talk about contextuality, like in the Speckens sense, in a hypergraph sort of framework, then what are the sorts of ingredients you're going to need to add to this framework to be able to do that, to build like a framework. And so once I give you the ingredients, I'll tell you how these can take you beyond like the Cabello, Severini, Winter framework. And hopefully you will take away something from this talk. That's the hope, yeah. Okay, so motivation. I think everyone here is motivated by like the whole reason people do quantum information or anything with the word quantum in front of it is typically to distinguish as opposed to something classical, right? But like people have, depending on which field of physics you're working in, you can often work with different notions of what's classical to you, right? Like for someone it might be classical mechanics per se. Some in more information theoretic terms, people will talk about like probability theories and like how classical probability is different from post-classical, like more general probabilistic theories. So there's various notions that people sort of have in mind when you use the word classical or non-classical. And here I want to talk about a very specific notion, which I'll call contextuality. In the literature, it's often called generalized contextuality, just to distinguish it from Kochen-Specker contextuality. And that will be a notion of non-classicality, okay? So firstly, why contextuality, right? So what are the desiderata you might ask of a notion of non-classicality? So I think the most basic one that, at least if you've done some quantum information, what you'd want is that the notion should be operational in the sense that I should be able to witness it from the data, if I did an experiment, collected some data, and I specified the conditions under which that data was collected, I should be able to just, make I want to reduce the number of assumptions I make about the theory that models my experiment, and yet be able to draw some non-trivial conclusions from that experiment about whatever the nature of the theory that describes this experiment is, right? So Bell's theorem is like an example of this, right? Like a very operational notion of non-classicality, which essentially needs just this sort of structure of relativistic causality, right? Like the fact that things can be space-like separated, and you can, in principle, forbid communication between them during the course of the local measurements. But you don't need to say much more about what's the theory that, I don't know, describes the two boxes on which you're doing your measurements. So it could be some general probabilistic theory. It doesn't have to be quantum theory, right? So in that sense, you can really reduce the number of assumptions you make about the theory that models your experiment in Bell's theorem. The second criteria we want in a notion of non-classicality is broad applicability, namely that you want to be able to use that notion to actually assess non-classicality in as wide a range of experiments as possible, right? Like you want it to be applicable to as wide a range of experimental setups as possible. Now, Bell's theorem, of course, satisfies the first notion very well, but the broad applicability notion is kind of not, depends on what you mean, but it's not satisfied in the sense that you need at least two parties and they have to be space-like separated during the course of the experiment. So it's a very special kind of experiment. It's not a generic experiment you might do in a lab, right? Like in a single laboratory. So in that sense, it's not broadly applicable. On the other hand, contextuality is broadly applicable because you can talk about single system non-classicality in this picture. And but it has a hard time being as operational as Bell's theorem. So like you need to invoke additional assumptions about like what's going on in your apparatus. Like you need to assume, for example, that it's doing projective measurements, for example, which is a very strong assumption sometimes. I think all the time. So for that reason, what we want to do is we want to take contextuality, which already is broadly applicable, and we want to make it as operational as we can. Like we want to reduce the number of assumptions that go into formulating the notion. Okay? Well, reduce or like find reasonable assumptions that like, a broad class of theories will satisfy in some sense. Okay, so that's what we want to be able to do. We want to be able to obtain noise robust operational witnesses of contextuality. So noise robust because in real experiments there's always some noise and you'll not always be doing projective measurements. Okay, so the framework, it's from this paper. It's 2005 PRA. It's called Contextuality for Preparations, Transformations, and On-Sharp Measurements. Note that the traditional Kochen-Specker notion is only defined for sharp measurements. By sharp, I mean projective measurements. Okay. Okay, so what's the basic setup? The basic setup is you can think of it as a prepare and measure scenario. Okay, so you have some device, some source device. So this is just an abstraction of many possible preparations you can do in the lab. And I can choose to prepare some, so this is a setting on this source device, some source setting. So I'll call this capital S the source setting. And when I choose a setting from some set of possible settings, then I'm instructing the device to prepare some ensemble of states. Okay, so my ensemble of states is labeled by this setting capital S. And the set of outcomes that are associated with this are these small s's. So these denote elements of the ensemble of states given by the setting capital S. Okay, so this is an input and this is like a classical output. So this is just a classical input, a classical output. This tells you what sort of it tells you what sort of system is prepared here. So this is like a quantum system or some general probabilistic system, some system that.
So I can think of that, for instance, the source is doing a measurement on
preparing an ensemble, for example.
State, and S gives us the result of the measurement, and then you get the quantum state coming.
So one of the ways to think of this.
Can be probabilistic.
Yes, exactly. So it's I mean one of the simplest ways to think about it is as one wing of Bell experiment. So if Alice is doing a measurement, she prepares an ensemble on Bob's side. Like if you only look at Bob's experiment, then every time Alice chooses a measurement, she's choosing a source setting for Bob in some sense, right? So that's you can have that picture at the back of your mind if it helps you sort of imagine what's going on here, right? So this is like a probabilistic device, like it outputs some states according to some ensemble, and then the system. So this is a non-classical thing. This is prepared according to this classical description, and it goes into the measurement device. Now something happens inside, we don't know what, but we choose something like a measurement setting on the device. We decide to make some intervention, and then we observe some classical outcome, right? Some measurement outcome. So this is a basic prepare and measure setup. I hope it's kind of clear what the picture I have in mind is.
So the capital A is a classical input?
Classical input in the sense is the label that tells you which measurement you're going to do. If I'm not a priori making assumptions about what's going on inside the measurement device, then it's just a classical label, right? But if I want to associate that classical label with a particular model of what the measurement inside is, then then I'll have to say more about what's inside the box. Right now I'm trying to work in like a black box type of situation, right? So all we have access to is like the classical interface with the device, which are two inputs and two outputs, right? A source setting, a measurement setting, a source outcome, and a measurement outcome. So those are the four things you have access to, things that you're going to observe and make your conclusions about, right? Okay, so if the basic setup is clear, then we can talk about what the setup means, right? Like, so the way I presented it, I was trying to talk of it in very operational terms. I was trying to say, all that one cares about in the setup is the probabilities of outputs given inputs, right? Like, what's the probability that I see a certain measurement outcome and a certain source outcome if my measurement and source settings were given as some specific choice, given by some specific choice, right? And of course, like here I'm assuming like that the source outcome is independent of my choices of interventions later on. So there is some sort of notion of causality built in. There is a time direction here, right? So there's no indefinite causality here despite my current job description, okay? Okay, so this is an operational description. Sorry, question? No, okay. So this is an operational description. Now, you can also ask, okay, but what does all this mean? Like, I mean, you're just collecting data. It's like, sounds very instrumentalist. It sounds like, you know, you don't really care about describing physics. And then one might ask, okay, so what's really going on? And that's the word ontological is supposed to, in some sense, denote what's really going on inside those boxes, like, you know. And so when people talk about an ontological description, they usually invoke these things called ontic states or hidden variables or physical states, whatever you want to call them, but you don't have to assume that this is the quantum state. This can be something deeper than the quantum state, something that describes all the properties of your system. Like, it's supposed to essentially frame the discussion in terms of properties of the system that passes between the source and the measurement device. That the assumption is that, you know, the things you're doing here, it's revealing some properties of, some intrinsic properties of this thing that passes between the two devices. That's not just about like the behavior of these boxes, but it's about like intrinsic properties of the thing that passes between these boxes, okay? And we denote those intrinsic properties by lambda. So then the picture is that every time you choose a source setting, you see a certain source outcome. That means you've sampled from some space of states. So this lambda lives in some space, some measurable space on which you can define distributions. So when I choose a source setting, see a source outcome, then I've prepared lambda with some probability. Okay, that's the picture. And of course, like, this source outcome occurs with a certain probability dictated by my device, like the way I sample. And so that's this thing, right? This is the joint probability of seeing a certain state lambda and the source outcome small s. Now, once that is given to me, this lambda goes into the measurement device. And so that means, given this lambda, I should be able to predict the probabilities of measurement outcomes given some choice of measurement settings. Okay, so this is all part of my underlying ontological model. Okay, so the reason I'm calling it an ontological model and not a hidden variable model is just because it's trivial to construct these things if, for example, you took lambda to be the quantum state, right? Like, then these would just be point distributions on the space of quantum states, for example, and this would just be the bond probability, for example. So I can always trivially construct such a thing if I wanted to, right? So there's no, so even though I'm giving you this whole story about how this lambda is passing between the two devices and its properties of that, and of course, like, you're averaging over this lambda because you don't have access to these distributions. This is part of your presumed model, right? Like, and so all you have access is to the operational thing. This is part of your model. Like, you're trying to explain why you see what you see in terms of these things. So, but at the same time, I haven't really added like any non-trivial assumptions about this ontological model so far, because as I said, you can trivially always construct such a thing if I just take my lambdas to be quantum states. Okay. So then we need to talk about what are the features that an operational theory must have for me to be able to define a notion of non-contextuality. Okay, non-contextuality is going to be my notion of classicality. So, you know, to note that classicality is non-contextuality and non-classicality is contextuality. Okay, so this is a slight. So every time I say non-contextuality, I mean a notion of classicality. It means independence of context in a certain specific sense. Okay, so now we're going to add some features to this abstract operational description. And so the first feature we need, so remember I was talking about invoking minimal assumptions about the operational theory describing the experiment. So I'm trying to describe what those minimal assumptions are for us to be able to make sense of our notion of contextuality, okay? So, because so far the theory is just a collection, it's like a data table. It's just inputs given outputs and the probabilities, right? I didn't give it any structure. Now I'm trying to give it some structure, and I'm trying to say that the theory must admit operationally equivalent procedures. Namely, there must exist source events in the theory, namely source outcome given some choice of source setting, like when you observe such a thing, that thing can be said to be operationally equivalent to some other choice of source setting and some other source outcome. So what do I mean by this? What I mean is just this, that regardless of what future interventions I might make on the source event, like by future interventions I mean the possible measurements I could do in my operational theory, I cannot distinguish between these two source events based on just the data, based on just the statistics that I collect. I cannot distinguish between these two things. So that means that these are operationally equivalent. For all experimental purposes, I cannot distinguish them, right? Even though I might have given them different labels, right? So that's a notion. So this induces a sort of like an equivalence relation on the set of states in some sense, right? So in quantum theory, actually I should talk about the second notion because this is the one that I'm actually going to use. So the second notion, so in quantum theory, for example, the analog of this would be like if the same quantum state appears in different ensembles of states, right? So the statistics of that quantum state is independent of the ensemble it comes from, right? So regardless of what ensemble labels that quantum state, like you cannot distinguish between those two things. The second notion is equivalence of the source settings themselves. So so this is a coarse graining. I'm trying to denote coarse graining over the outcomes here. So if I sum over the outcomes of an ensemble, so I just look at the average state associated with the ensemble. I'll call two ensembles in some sense, two source settings operationally equivalent if when I sum over the source outcomes, there's nothing in the statistics that distinguishes them. So an example of this in quantum theory is when you have like a given density matrix and you consider two different convex decompositions of it, for example. Okay, so that's an example of like when source settings might be operationally equivalent. So that's the minimal structure we need on the side of preparations. On the side of measurements, again, we need some equivalence relations. Okay, so we need situations where like a measurement event is operationally equivalent to another measurement event, in the sense that there is no source event that I can like prepare. Like there's no way I can prepare the system that will distinguish between these two measurement events. Like there's nothing in the data that distinguishes them, right? Again, in Kochen-Specker theorem, the notion of what these equivalences usually correspond to the fact that the same projector may appear in two different choices of measurement bases, right? Like two different measurements, but they share a projector, for example. So that means, like for that projector, the statistics is independent of which measurement you were doing actually, right? So that's a notion of an operational equivalence. I'm trying to make like this discussion I'm trying to keep it abstract. I'm not talking too much about quantum theory because eventually I want to like talk to you about witnesses of contextuality that do not assume like the full structure of quantum theory. They try to assume like just these basic features that I'm talking about right now, okay? So we have a prepare and measure scenario, we have an operational description, we have equivalence classes of preparations, equivalence classes of measurements. Now we need to define what a context is, okay? If you want to talk about non-contextuality, we need to define what context means, right? So what are the kinds of things that we treat as a context in this description? So namely, any distinction between operationally equivalent procedures will be taken to be a context, okay? So for example, as I said, like, you know, with preparations, so if this is the space of preparations, all these preparation devices, even though they may look different, they do the same thing. The statistics that they produce, you cannot distinguish them, okay? So that means they fall in the same equivalence class. So any distinctions between them are differences of context, right? So distinctions could be, an example of a distinction is which ensemble you use to prepare your density matrix, right? Like what ensemble was averaged to give you your density matrix. So that's an example of a difference of context. These could be different ensembles which give you the same density matrix, right? And you can also have like trivial notions of context. For example, the color of the device, for example, right? No one actually works with that notion of contextuality in like because usually we assume that the color of the device is not relevant for my description of what's really going on in terms of the physics, right? So, but that notion will also be in some sense incorporated in this. Measurement, for measurements, again, the same picture, right? Like you can have, so you have these islands, like these are equivalence classes of procedures. Procedures which in the lab they look different, but when I look at the statistics, they're the same. Basically, that's the point, right? So a context will be any distinction between operationally equivalent procedures. So examples, preparation context, I've already told you this, different realizations of a given quantum state, for example. So qubit, a maximally mixed state, can be prepared in infinitely many ways. Here are two of those, right? So these are two different preparation contexts for a maximally mixed state on a qubit. One is a Z basis, the other one is an X basis, for example, right? Measurement context, as I already said, different. So the more general notion would be like different realizations of a given POVM element, right? Of a given POVM or a POVM element. An example of this is the same projector appearing in different bases. Okay. Okay. So prepare and measure scenario, operational theory, equivalent structure on sources and preparations, definition of a context. Any difference between things in an equivalence class is a notion of context. Now we can talk about non-contextuality. Okay. So far so good. Like. Okay, so now I can define the notion that I need. Like everything I talked about so far were prerequisites to be able to define this notion. And non-contextuality will be taken to be motivated by this idea of, I think it's due to Leibniz, like the idea of like the ontological identity of like empirical indiscernibles in some sense. For short, I'm just calling it identity of indiscernibles. And I mean, you can look at this nice essay that Rob Speckens put out like recently, like a few months ago, which is about like motivations of how this idea is motivated in some sense from both Leibniz and how Einstein used this idea in trying to formulate general relativity. So here you're trying to motivate, like based on same philosophical grounds, you're trying to motivate a notion of non-contextuality, okay? And the notion is that if there exists no operational way to distinguish two things, two procedures, so I'm saying it very colloquially here, two procedures, then they must be physically identical. That really, if I can't do an experiment to tell two things apart, then in my model of those two things, in my model of physics, like the description of what's really going on, I should treat them as the same. That's what one is trying to say, right? Like I can't do an experiment to distinguish them, therefore they're the same thing. In fact, no one can distinguish them, so it's not just me, but like in principle, like there's no experiment in the world, like given my current theories of physics, no one can distinguish them. So therefore, if I'm looking for a deeper description, I should really unify these two different things as like one thing in my deeper description, right? Maybe like if you read it in the contrapositive, it seems more intuitive to you. Like, so this is the same as saying if two things are non-identical, that if there really is a difference between them in terms of the physics, then there must exist an operational way to distinguish them, that I must be able to do an experiment to tell that difference, right? Okay, so that's the notion that we're working with. How is it relevant to what we're talking about? The way it's instantiated here is in terms of, so the first notion is measurement non-contextuality, which is given the operational equivalence of two measurement events, namely that there's no experiment that will distinguish them. You assume, so this implication is sort of an assumption of non-contextuality, that if this is the case, then in my model of reality, like the lambdas, which are supposed to be a deeper description of what's really going on, even the lambdas cannot distinguish these two measurement events, okay? So that's the sort of assumption one is making. It's a hypothesis about the ontological model. And so now I'm adding some constraints on that, you know, that lambda decomposition of that operational probability, right? Like I said that there's no constraints on it like initially because you could just take it to be the quantum state. You can still take it to be the quantum state, but the question is, can you satisfy these assumptions of non-contextuality if you took it to be that? Turns out that you can satisfy this, but you cannot satisfy the second one. So the second notion here is preparation non-contextuality, which is that, again, you know, you can't operationally distinguish two things, two procedures, then treat them the same way in your ontological model. So which means that in the ontological model, the distributions look the same over like the way lambda is sampled, right? Again, so here when you coarse grain over the outcomes, then it means just this, okay? So far so good. Like so the idea is it's an inference from the two operational description to the ontological description. That's what non-contextuality is. This is the operational description, this is the ontological description. Based on things I've observed on the operational side, I want to put constraints on the ontological side. And I want to ask, can I build a physical theory which satisfies, like a deeper model of quantum theory which satisfies these two assumptions, right? because it'll be satisfying if it's the case that things that look different, like if you look at the formalism of quantum theory, like, you know, two ensembles look very different, but like if I average them, they give you the same density matrix, so it's basically the same thing. So if I'm trying to give a deeper description of this density matrix, I should really assume that it corresponds to the same distribution over ontic states, right? Like that's the sort of thing you're trying to implement here. So I just want you to, I just want to check if people think that this is an intuitive notion of, you know, we'll take this to be a notion of classicality, that if we're building like a notion of, like, we take this to be a notion of like, you know, what a reasonable physical model of, an underlying model of, you know, an experiment should be.
I don't.
Okay, yeah. But like, okay, yeah, sorry, go ahead.
As you said, lambda could be the quantum state.
Yeah.
And that would be.
So when I take that to be the case,
Yeah.
it turns out that when I construct hidden variable, when I construct an ontological model, like just that naive ontological model that you're talking about, that's actually called, I think in the literature it's called the Beltrame-Bugarski model or something, where they take the space of lambdas to be like pure states, and the probability rule that defines these probabilities is just the Born rule. So it'll just be the trace of like the operators associated with this thing times rho lambda, like lambda is associated with a quantum state, right? So in that picture, it turns out you can satisfy the assumption of measurement non-contextuality, but you can't satisfy the second assumption. So that picture of reality where you take a quantum state to be your fundamental description of, like, to be your lambdas, it's preparation contextual. Like it'll basically introduce distinctions between preparations that are otherwise the same in terms of the operational statistics. So it will have to distinguish between the Z-basis preparation of the maximally mixed state and the X-basis preparation of the maximally mixed state. They will be represented differently in the model.
Because of Bell's theorem, basically.
And yeah, you can also think of it as in terms of you can think of it in terms of Bell's theorem as well, if you wanted to.
One tries to do it with mixed states.
So I may have some supplementary slides which will probably show you this model explicitly, but can we like leave that to later, because I think I promised too much and I don't have much time. So I want to just quickly go through the formalism, and then we can like go to this at the end if there's a little time, right? So for now, all I wanted to say was that the model you had in mind doesn't satisfy these two assumptions. That's all I wanted to say. Okay. Okay. So, what is Kochen-Specker non-contextuality? So, given the definitions I've given you, in terms of these definitions, Kochen-Specker non-contextuality is the conjunction of two assumptions. One is measurement non-contextuality, that your, you know, measurement events which are operationally equivalent should be represented by the same distributions, and the additional idea that the distributions should be deterministic. So outcome determinism is the idea that lambda tells me exactly which outcome is going to happen. Okay, I need both of these assumptions to see the Kochen-Specker contradiction. Okay, and here's an example. So for Shantanu, I guess, who hasn't heard of this before, or whoever has not heard of this before, this is a simple example of the Kochen-Specker theorem. Here we are looking at like a 4-dimensional Hilbert space, and we are looking at so each vertex here is like a vector in this Hilbert space, or you could take it to be the projector, like the ray, projector corresponding to the ray. And each loop here is like an orthonormal basis. Okay, so there are 18 vectors which have been partitioned into like 9 orthonormal bases. So there's first, second, third, fourth, fifth, sixth, 7th, 8th, and 9th. So there are 9 measurements, okay? And there are 18 vectors which have been partitioned into these 9 ways of measuring things. Now remember, when we talked about measurement non-contextuality, the idea is that if the same projector appears in 2 different bases, I want to assign it the same probability in my hidden variable model, in my ontological model, right? Further, I want this probability to be deterministic, like that was the second assumption in Kochen-Specker non-contextuality, right? So that means I have to tell, my lambda has to tell me which outcome occurred when I did a certain measurement, right? So let's say lambda decided that this outcome occurred when I did this measurement or this measurement, right? So I represent that by a black dot here. That's like a probability of 1, right? So that means I have to put a 0 here and a 0 here, because these are exclusive events, like they cannot all be assigned, like things have to be normalized basically, right? So these are 0 and these are 0. Now let's say lambda decides that in this measurement this outcome is going to happen. So that means these two are 0, and in this measurement these 3 are 0, right? Is that okay?
Yeah.
And similarly on this side, I say that, okay, this outcome is going to happen. That means that these are all 0 and these guys are all 0, right? So I'm just like following those basic rules of what the assumptions ask you to do. And then you're basically stuck, because you have to choose like which of these events is going to happen, because this we know cannot happen because of this. And this we know cannot happen because of this, right? And this, so we can either choose this one or this one, right? So let's say I choose this one. So that means this cannot happen and this cannot happen, but then that means that, you know, this thing is left subnormalized, like my model cannot predict what's going to happen here, right? Like it's not a valid assignment.
It says that nothing is going to happen.
I mean, if you want to interpret, you can interpret it in, like, then that means you're going to a 5-dimensional system, because then there's some extra space where nothing can happen, right? Like, these are supposed to be exhaustive.
It's a contradiction.
Yeah. So what I'm trying to say is that if you try to assume, stick to these assumptions and try to assign these outcomes, then you cannot do that, no matter how you start. An easy way to see that is that there are 9 bases. So there have to be 9 assignments of 1s to these bases. At the same time, each vertex appears in 2 bases, right? So that means the number of 1s should be even. So an even number will not be equal to an odd number. So combinatorially, this is just not possible, right? So that's a classic example of the Kochen-Specker theorem. Okay.
Irrespective of like the dimension of the Hilbert space.
So if you go to a higher dimensional Hilbert space, so in every Hilbert space, I'm not sure if this has been proved, but I think in every Hilbert space you can construct such Kochen-Specker sets. Like you can construct sets where it's impossible to assign outcomes in this sense, right? So that's so we call this a logical proof, because this is basically I did not need to collect any statistics. In 2 you cannot construct this, yeah. In 2 dimensions you cannot construct this with like projectors, okay? And the reason you cannot do that is because you don't have a non-trivial notion of like different contexts, because if I choose a projector, the other one is fixed, like it cannot appear now. That's why you cannot do it in 2 dimensions. The second kind of proof of the Kochen-Specker theorem we call a statistical proof, which is more like Bell's theorem in some sense, because here you need to look at probabilities and then put constraints on them based on these assumptions. So here, like, there are 5 measurements and each has 3 outcomes, and we're only interested in these 5 projectors of these outcomes, okay? So we pick like what we're interested in. So we look at the probabilities of these 5. And the question is, what kinds of probabilities can a model which is non-contextual assign to these guys, right? So that means I have to tell you which outcome occurs, like with some probability, like 1 or 0. It has to be deterministic. So if I assign this a probability 1, then these two have to be 0. But then if I assign this a 1, then this has to be 0. So that means at most 2 of these can be made 1, right? Like at most 2 of these projectors can occur, like if I was working with a non-contextual model. Now all deterministic assignments will not do better than 2. Like it's basically the independence number of this graph, if you know what that means, right? Like the number of non-adjacent, maximum number of non-adjacent vertices in this graph. So that gives you a bound on the sum of these probabilities, regardless of what the, yeah. Yeah, the middle dot is like, because it's a 3-dimensional system, right? So there are these 2, and this is just the complement of like pi 1, pi 2, right? So you can treat them as like no detection events or things you're not interested in, like you're only interested in those other probabilities. Okay, so so there's logical proofs, statistical proofs. The CSW framework tries to essentially say that this is an example, which was due to Klyashko and others, But you can actually extend this to like a whole family of graphs and hypergraphs, and you can write down bounds in terms of graph invariance. Like, so here I gave you a bound. I said the sum of these 5 probabilities will be less than or equal to 2. That thing is generalized to say something like, if you write down a function of this form, then the bound on that will be given by the independence number of whatever the underlying graph is. Okay, I'll write that down so that it's clear. I don't know how much time do I have? So 15 minutes. Okay. So I may have to rush a bit, but well, whatever I'm able to explain well, I'll do. The rest I'll do in the last 1 minute. Okay. Okay. So when I talked about those 5 events, they were drawn from. So the CSW framework visualizes those 5 events as drawn from a bigger experiment, where in fact you're doing these joint measurements in some sense, right? So there are 5 basic measurements like M1, M2, M3, M4, M5, and then you're doing joint measurements in a cycle. So M1 and M2, M2 and M3, M3 and M4, M4 and M5, M5 and M1, right? So these are those things, okay? And they'll have 4 outcomes because each of those measurements, okay, I've suppressed some outcomes here in some sense. In any case, so think of this as that sort of picture, okay? And we'll draw. Oh, I wanted to introduce the notion of what I mean by a contextuality scenario. Let me not get into the specifics of that example. So I'll call a hypergraph gamma, where like the vertices of the hypergraph will denote measurement outcomes. So each vertex is a measurement outcome, just as it was in that 18-ray example. And hyperedges denote measurements. So each hyperedge is a complete measurement. Okay, so the probabilities have to add up to 1 for that measurement, such that of course the union of these edges covers the full vertex set. So that's just the formal notion of what a contextuality scenario is. If you look at the Cabello-Severini winter paper, they draw a diagram like this for like as the underlying description for Klyashko, and then they draw 5 events. They draw this event, this event, this event, this event, and this event. Like those projectors correspond to these 5 guys: pi 1, pi 2, pi 3, pi 4, pi 5. Okay, at the corners. And now if I give you this contextuality scenario, then I can construct an orthogonality graph for that. An orthogonality graph is just like converting that graph to hypergraph to a graph by connecting any 2 vertices which appear in the same hyperedge. Okay, so I draw a line between them whenever they appear in the same hyperedge. That's what an orthogonality graph of this thing is. So these are notions that will go into the inequalities that I'll write down for CSW. So that's why I'm introducing them. So now you can talk about probabilistic models on this gamma. You can talk about what are the ways I can assign probabilities to these vertices. And so a probabilistic model is a map from the vertices to probabilities such that every edge, hyperedge, is normalized, right? Like the probabilities have to add up to 1. And for all the hyperedges, and the set of all probabilistic models on gamma, we will denote it by G of gamma. And G of gamma is just supposed to denote like general probabilistic models. So models that satisfy these 2 constraints, that their probabilities and add up to 1 on the hyperedges, they're all possible probabilistic models. Now there are 2 relevant subsets of this set of probabilistic models that are of interest. One is the Kochen-Specker non-contextual models. So these are the models that satisfy those assumptions we were talking about, right? So they will be convex mixtures of these deterministic assignments, right? So whenever you can do deterministic assignments, you can define such a set, right? This set will be empty for that 18-ray example, for example, like that I was talking about, right? But it's non-empty for that 5 vertex example, okay? The second set is what in the literature is often called consistently exclusive or consistent exclusivity. And this set of probabilistic models is such that, so the constraint is essentially like, you relax certain things. So here you're only requiring that for all cliques C in the orthogonality graph, these probabilities have to add up to less than or equal to 1. And essentially this is supposed to be motivated by the idea that if you're given a set of projectors and if they're pairwise orthogonal, then their sum of probabilities will always be less than or equal to 1. That's what it's motivated by. Like it's just abstracted away that motivation, but that's where this constraint comes from. Okay, and so it's the case that these containment relations hold. That the classical, so C is often taken to be classical here. Kochen-Specker non-contextual is contained in this set. This is contained in this set, and the quantum set is somewhere in between. Like if you're looking at like just the projective measurements in quantum theory. Okay. But we want to go beyond projective measurements, which is why I didn't talk about the quantum set. Because if you go to POVMs, the quantum set is the same as the set of general probabilistic models. Because you can realize any general probabilistic model using trivial POVMs if you wanted to. Question? So in CSW, they call there's something called the exclusivity graph, which is supposed to be a subgraph of this big orthogonality graph, where I choose 5 events, for example. And I construct some linear sort of functional which maps like these probabilities, like it weights them by some numbers, and it computes some value. And this value will be basically bounded for different theories. Okay, so this is the analog of like your Bell functional in this picture. Okay, and so the main result of CSW is that by Kochen-Specker non-contextuality bounds this functional by this graph invariant, this independence number of the graph with weight W. So for example, in that 5 vertex example, we just took W's to be 1s. We just took sum of the 5 probabilities, right? So there the independence number was 2. That was the maximum number of non-adjacent vertices you could find. The quantum, so when I say quantum, it really is about like when you associate vertices with projective measurements and not like arbitrary POVM elements. Then the bound is given by this thing called the Lovász theta number. I won't give you the definition, but it's basically the thing you would get if you maximize over quantum assignments. Well, it's an upper bound on that. And the last one is basically something called the fractional packing number, which is the algebraic maximum in some sense in these assignments, like of this value. So for example, for that 5 vertex case, this is 5 by 2. So this is what is happening in KCBS. We take this to be 1 for all V. Alpha is 2, so this is like the classical bound. Theta is square root of 5, that's the quantum bound if I'm looking at projective measurements. And alpha star is 5 by 2, so that's like the general probabilistic bound, right? So that's the hierarchy there. Missing ingredients. So missing ingredients in the sense that if I want to formulate what I introduced initially, like Speck's contextuality in this way, then what am I missing? So firstly, measurement non-contextuality will only give me like this trivial upper bound of alpha star. Like the role of measurement non-contextuality in this framework, like in the Speck's approach, is that it gives the structure of these probabilistic models, right? Like it lets you assume that the probabilities you assign to these vertices is independent of which hyper edge the vertex appears in. That's what it lets you do. So it gives that structure to the set of probabilistic models. That's the role it plays, but it doesn't put any more constraints. So, and we don't want to assume determinism. So what do we have left? We have to use this second assumption, which is preparation non-contextuality. And so far, I've not made any use of non-trivial, operational equivalences between preparations when I was talking about CSW, because they don't talk about preparation non-contextuality. It's not part of the traditional framework of Kochen-Specker contextuality. So I'll just briefly mention how these things are introduced. So these are the hypergraph ingredients. How much time?
Minus 3 minutes.
Huh? 7? Okay. Okay, so contextuality. So maybe I'll take 4. 7 minus 3 is 4, right? Okay, so the way this framework works is that you take the exclusivity graph of CSW, you convert that into a smaller contextuality scenario than that big gamma that we had initially. Basically, so you add an extra non-detection vertex to each hyper edge, and you turn maximal cliques in G into hyper edges. Okay, so maximal cliques are like cliques which are not contained inside other cliques. So we can take these probabilities to be probabilistic models on these things. Okay. a second ingredient we need is a certain invariant which is associated with this hypergraph, which I call the weighted max predictability, which is the idea that you take in a given probabilistic assignment, you take the max probability of each measurement and you weight it by some weights, which are these QEs, and this is like the max probability for in a given hyperedge E. You average that with these weights, and then you take the max over all indeterministic assignments. Okay, and so this is just the sum and substance of this is that this is a number you can compute given a hypergraph. Okay, and it's an invariant that I'm adding to like the alpha stars that we had in the CSW framework. So this is the new definition, and this turns out to be relevant to the inequalities we write down. And I apologize because like I think this will take a lot more time than I have, and so I'm just gonna like end with saying, well, I am going to end. Because we want to add sources, what we'll add is for every measurement, we had 3 outcomes, right? So each of those outcomes can be made predictable on a corresponding eigenstate, right? If you're thinking in quantumly, every projector in an orthonormal basis is deterministic on its corresponding eigenstate, right? So think of these as like those eigenstates, right? And so if I take a uniform mixture of these 3, then I get the maximally mixed state on a 3-level system, for example, right? And similarly, so these all correspond to the measurements in some sense, right? So the idea is that I'm using these source events to benchmark how predictable my measurements are. So in general, my measurements are not going to be projective. They're going to be some POVMs, right? And each POVM the probability of like that thing occurring will be maximized by one of its eigenstates, right? Like, so I take it to be that thing. And similarly for the other one and other one. But it won't be one in general, right? Like, so there is some, because of the non-projectiveness, I will see that by invoking these additional preparations. So yeah, so you have this measurement scenario, this source scenario, and you match. So this thing can be made predictable on this thing if it's projective, but not otherwise. And so this quantity kind of captures that fact. Like, so this is about source measurement correlations. So I look at the correlations between measurement outcomes and source outcomes when I choose like the same settings. So the correlation between this thing and this thing, what's the probability that this thing occurs, and this thing occurs when the settings are this and this. So this will be 1 if like, you know, I'm working with projective things. So this quantity will in general be 1 if everything is projective and pure. Okay, but when things are noisy, then this will be strictly less than 1. So once you have these ingredients, you can combine them in a way which I haven't specified how you combine them, but you can put them together to come up with this what I call noise robust witnesses of contextuality, and that changes your original inequality, which was of this form, like that this thing is bounded by alpha, by this sort of a correction sort of term, which involves, most importantly, like that source measurement correlation term. So note that this correlation term is going to be, the more projective your measurement is, like the more projective you can make your measurements, this is going to be closer to 1. So when it's exactly 1, then this term disappears and you go back to your usual inequalities. But if you have noisy measurements, then there'll be some penalty. Like you need to work harder to violate this non-contextuality inequality. And if you have like really noisy measurements, the inequality will become trivial at some point and you can't violate it anymore, because there's just like, you know, it doesn't teach you anything because there's too much noise in your experiment. That's the intuition here, okay? These invariants are the same as like the CSW invariants. This is the probability of sampling the state on which you do the measurement. And this beta is that invariant that I had defined. So this is how they eventually come together, all of these things. So for the CSW case, it means that the inequality looks something like this. So it's 2 plus this correction term, okay? Under some choices of parameters, this can become trivial, and that's when it tells you that there's too much noise, basically. So again, the framework, so this, what I talked about applies to cases where this thing is non-empty, where there's some classical models, and where this thing holds. So alpha star can be seen as an upper bound only when this is true, on the gammas. Okay, so this is just the scope of what kinds of gammas we are looking at. On the other hand, if you look at these gammas where this thing is empty, which is this 18-ray construction, for example, then for that, if you construct like these noise-robust witnesses, then the only relevant invariant is this beta. Okay, and recall that beta was we have already defined, and all the inequalities in this other, like the logical proofs, they translate to inequalities of this type. They translate to bounds on this source measurement correlation given by this invariant beta. And so for that 18-ray case, you can write down an inequality which looks like this. The important thing to note is that this thing is strictly less than 1. So there's a gap between 5 by 6 and 1. So if everything was projective, then the score would be equal to 1. And you'd have like your ideal Kochen-Specker contradiction. But when you're away from projectors, you're doing some noisy measurements. In this, as long as your noise doesn't lower your core value below 5 by 6, you still witness some non-classicality, is what I'm trying to say. So the Kochen-Specker theorem becomes inapplicable the moment you move away from projective measurements, but this kind of gives you a sort of a region in which you can witness something interesting. And so you can study properties of this beta from the structure of the hypergraph. I tried to study it in this paper. There's lots of interesting things there. This is my final takeaway. So broadly speaking, we have like these two. So this was about logical proofs, like this paper. This was about statistical proofs, like, so this is 18 vectors, this is like 5 vectors. And then these two papers are basically developing like the corresponding hypergraph frameworks. So this is like a generalization of the CSW framework, and this is a hypergraph framework which doesn't have an analog in the previous literature, but it gives you inequalities of that core less than or equal to beta form, and it studies like properties of this hypergraph invariant. So people interested, if someone's interested in graph theory and things like that, I would like to understand like what this hypergraph invariant might be useful for outside of contextuality, for example, because I mean the definition is motivated by what I'm doing, but I believe that it should be useful in elsewhere also. Open questions you can talk about. I probably don't have enough time to talk about these, but thank you. No, I think you have a talk, right?
Yeah, sure. I meant another time, perhaps.
Okay, yeah.
We have time for questions.
Yeah, go ahead. Yeah, if there's time.
There was one thing which some time ago, but I think it was David Kent and others had some ideas that Kochen-Specker theorems were
Nullification.
Robust to noise.
Exactly. Yeah.
What is the relation with what?
Yeah. So I did not talk about that because that discussion like will add another half an hour to my talk. But the result there, the Meyer, Clifton, Kent, like I think those are the set of models that they constructed. So there the claim is that in any Hilbert space you can always find a dense subset of projectors in the space of all projectors that you can color according to the Kochen-Specker rules. So because there exist these dense subsets in all Hilbert spaces, you basically can never test the Kochen-Specker theorem because you can always approximate like any of those vectors arbitrarily well, like to whatever precision your measurement is. So as long as your measurement has a finite precision, your experiment has some finite precision that you will, like you assume that you're always delta away from like what you want to do, right? As long as that delta is greater than 0, you can prove that there are color. So how does it translate for this? The way it translates for this is that this operational equivalence, which is between this projector appearing in this basis and this projector, so this is one implementation of this projector, and this is another implementation of this projector, right? Those two implementations may not be exactly the same. So that means this link breaks, like I have to separate these two things so that the whole thing becomes KS colorable. Like I can color it because I cannot identify these two things anymore. So then I can assign ones and zeros without any contradiction. So that's the way it translates here is that basically these links break and then you cannot have a contradiction. So that's the quick version of what like all of those papers of Meyer, Clifton and Kent do. They basically I mean I haven't gone through the proofs myself, like how you construct those. They actually give like explicit models which will reproduce quantum theory to arbitrary precision and things like that. So so that's what happens there, and the way this problem shows up in this operational way of that we are talking about. So for example, when I was saying I don't want to assume too much and all that, like we did not want to assume Hilbert space structure, for example, right? But the way that issue shows up, the operational incarnation of that issue here is that this implementation of this projector could still be inequivalent to this implementation, right? So I still don't have my argument. So what do I do? So what we do, at least like the way, so in one of, so there's only one experiment that we did based on these ideas. And in that experiment, we invoked some additional assumptions about the theory beyond what I mentioned in this talk. And one was the assumption that the theory is convex, like namely that if I've done a set of procedures in the laboratory, then I assume that the theory that describes my experiment is such that I could have in this experiment done anything in the convex hull of procedures that I did, like because that's just like classically mixing noise and things I already did, right? So I assume that the whole convex hull is accessible to me, and then in that convex hull, I look for not the original projectors that I wanted, for example, but some noisy versions of them, but which happen to be operationally equivalent. So that's like roughly the idea, and so that restores this structure. But you lose the projective property, like you no longer have like those exact things you needed. And so we need convexity so to get away with like these inequivalences. We basically say, okay, the things you did in the lab did not satisfy these equivalences, but in the convex hull of things you did in the lab, there are things that do satisfy these equivalences, but which are like noisy. So you pay a penalty for picking those noisy things, which means it becomes harder to violate your inequalities because you've added noise. But you've satisfied the premise of everything you're doing because you needed that equivalence to be able to invoke non-contextuality. Otherwise, if there's no equivalence, there's no reason, you have no reason to talk about non-contextuality. So that's the quick summary of like the Meyer-Clifton-Kent. I mean, it's definitely quite interesting, like the Meyer-Clifton-Kent results, like in terms of how you understand, because essentially what they're saying is that, you know, there are dense subsets of like these projectors such that like the probability rule associated with them is not like the Bond rule, but it's just like completely classical. It's you can think of them as reductions of like a big measurement in some sense. So it's interesting in that sense. It seems like, you know, the Bond rule only shows a difference for like things which fall outside these dense subsets. So anyway, so yeah, sorry, go ahead. Matthew, you wanted to give your talk.